In this session we'll continue with the analogy, the reinterpretation, the rewriting, the way of seeing a wave function as a vector. So it's been the theme pretty much for the last couple of sessions, and it's mathematically very convenient because then you can take over all the mathematics of vector spaces, and in particular there's a particular kind of vector space called a Hilbert space, which is a large branch of mathematics with all kinds of techniques and tools that you can use in the context of quantum mechanics. So in that context, let's be a little bit more specific. So the theme of this session will be mapping, or translating if you like, wave function language into vector language, and operations in with wave functions, for example superposition and overlap integrals and so forth. We can translate those things into manipulations with vector spaces, with vectors, right? And so here's our first example. So let's interpret or translate or think in terms of the overlap integral. So we can think of the overlap integral as a scalar product, a dot product. Remember from vector calculus, scalar product and a dot product, same thing, just two different labels. Similarly, the cross product is a vector product, because when you cross two vectors you get a vector. When you dot two vectors you get a scalar, just a number, right? So scalar product or dot product of just two functions, two wave functions. Okay? So translate an overlap integral, right? So that's psi m star times psi n integrated over the volume. So that's your overlap integral, and think of that as now a dot product of two vectors, where you're thinking of your wave functions now as vectors. So if you dot product these two vectors, then you can think of that as the overlap integral, or vice versa, either way. You're talking the mapping between two languages, in a sense, right? So, for example, here's in wave function language. Talking in terms of wave functions. So here you have a superposition. So you're adding wave functions, weighted. You multiply each wave function by some complex number, and then sum the whole thing. So that's a superposition wave function here. And you can think of that. Now if you think of the wave functions here as unit vectors, like you can rewrite that as E n hat, or I could make that I. Okay? So you're translating, in a sense, your wave function into a unit vector. That's the main idea of these sessions. Think of the wave function as a vector in a vector space, right? So that means you can rewrite. Here is your overlap integral. So think of that now as a dot product of unit vectors, where your this unit vector here, that's the translation, if you like, of the wave function psi m, and that would be the wave function of psi n. Okay, and the dot product corresponds to taking the integral of these two wave functions. Okay, now this is the result of this, we're assuming now that these two wave functions are distinct, the spatially separate in this. That's not the right word. Their integral. If m and n are the same, then this overlap integral is 1. The overlap is total, obviously. And if m and n are different, then this integral comes to be 0. So in other words, the value of this overlap integral is either 0 or 1, depending on whether m equals n or m is not equal to n. So in other words, this overlap integral has the values of the delta function, right? Delta mn. Okay? So summarizing a little, so you're translating wave functions into vectors, and you're translating dot product of vectors as the overlap integral. Okay? You're mapping two languages, the language of wave functions and the language of vectors in a vector space. Okay? So here's the main idea. You just think of a wave function as a vector, and then you can use all the tools, all the mathematical tools of vector space theory, and that's a big topic in pure mathematics. All right. Now, within physics, a British guy, Dirac, Paul Dirac. Story goes, I think his father's French, and they were living in Britain, and his father insisted that Paul Dirac speak French at home when he was small, but Dirac lived in Britain, so he knew English, and he didn't know French very well, so he just chose to be silent. So he grew up like that. I think it affected his brain. So Dirac was particularly taciturn, very silent, non-speaking sort of person. Anyway, a genius, Nobel Prize, one of the fathers of quantum mechanics. Now he invented a notation for the overlap integral. It just simplified things a lot. So instead of writing the overlap integral this way with an integral sign, psi m star psi n, delta d volume, the differential of volume. So this is the integral form. He just simplified it by using angular brackets that look like this. Like if you look at the left side, so the left angular bracket and a vertical line, he called that a bra, B-R-A. And if you look on the right part, so you get a right arrow and a vertical line, you call that a ket, K-E-T. So obviously if you put these two together, so bra ket, it's a bit of a physics joke. Physicists like inventing humorous terms in their topic, like in particle physics and cosmology. You study the cosmos, study the universe. There are things like WIMP, W-I-M-P. That's a weakly interactive massive particle, and in ordinary English slang, a WIMP is a weak person, either physically weak or in terms of courage, rather cowardly. So that's a WIMP. And then a bit later, physicists also invented the word macho, M-A-C-H-O, which is sort of the opposite of a WIMP, sort of a male who over-asserts his maleness, sort of like Mexicans and South Americans are known for being macho. And now it's an acronym, macho. I'm not quite sure what it stands for, but I think the HO part of it is halo object, M-A massive. I don't know. I don't know what macho stands for, but WIMP and macho. And there are terms like gluons that glue things together, and quarks, and The physicists like doing this. Maybe Dirac helped create a tradition with this sort of joke, bracket. So, so this is what a bracket looks like when you put them together. So you just, instead of having two vertical bars, you just have one. Now what goes in here, in this space here, would be your psi m, and what goes here would be your psi n. And the fact of these two angular brackets